Hello everyone, my name is Garvesh Sharma and today I am here to represent a topic that is UV, visible and fluorescence spectroscopy. So let's start. Okay, so here the main thing that we are taking into consideration is electromagnetic radiations. As we all know, electromagnetic radiations is made up of photons. A photons is the smallest or the simplest unit of a light and it carries energy. ठीक है? And electromagnetic radiations has a certain characteristic parameters by which it is measured. It has frequency, wavelength, amplitude, etc. So let's start with the frequency. So frequency is defined as number of times electric field radiations oscillates in 1 second. इजी लैंग्वेजेस के अंदर में हम बोल सकते हैं कि एक सिंपल 1 सेकंड के अंदर में इलेक्ट्रिक फील्ड जितना ऑसिलेट करेगी that is considered as frequency, that is and its SI unit is hertz, 1 hertz per cycle. And the second aspect of the electromagnetic radiation or second parameter is wavelength. It is the distance between the two nearest parts of the wave in the same phase, and the relationship between the wavelength and frequencies can be written as C is equal to mu lambda. And as we all know that photon is subjected to energy, so its energy equation is given here, that E is equal to h mu or h equal to hc by lambda. Here h is the Planck constant which has a fixed value, that is 6.626 into 10 to the power minus 34. Okay, so here in this figure it is the ear spectrum is shown. So we can clearly see that the visible spectrum starts with 400 nanometer wavelength and it ends with the 700 nanometer wavelengths. There are many other types of radiations, that is gamma rays, ultraviolet rays, infrared rays, microwave rays and radio waves. So what is spectroscopy? It is the branch of the science which deals with or which studies with the ER interaction with the matter. कि basically जब आप ER की interaction with the matter, either with the molecular level, either at atomic level, either at a subatomic level, when you are considering those things, the study is known as spectroscopy. It is of two kinds, atomic and molecular. In atomic spectroscopy, we are studying the interactions of ER with the atoms, and in case of the molecular spectroscopy, we are studying the interaction between the ER and the molecule. Okay, so principle of spectroscopy. A very simple principle is कि when a molecule absorbs a certain kind of a light or of certain frequency or a wavelength, it gets excited from its ground state. Its electrons gets excited, in other words, from its ground state, and went up to at their higher electronic states. And when they are returning back to the ground state, they release certain kind of an energy in terms of light of certain wavelength and frequency. And when these intensities of the absorbed or emitted radiation is graphed against wavelength or a frequency, a certain kind of a spectrum is achieved. And spectrometer, it is an instrumental designed to measure the spectrum of a compound. Okay, so here the absorption spectroscopy and emission. हमने जैसे बात करी कि absorption में जब basically एक molecule है या एक atom है, when it absorbed a certain kind of a light, so that analytical technique which conserved with the absorption is considered as absorption spectroscopy, such as UV visible and infrared spectroscopy. In case of emission spectroscopy, when a certain kind of a substance emits a certain kind of a wavelength of certain frequency or a wavelength, it is considered as emission spectroscopy. For example, mass spectroscopy. Here the Beer-Lambert law, spectroscopy के अंदर में it is the most important law. It states that absorption is directly proportional to the concentration of the solution. Here A is equal to के अंदर में A is equal to epsilon L C, where L is the path length and C is the concentration and epsilon is the molar absorption coefficient. In figure we can see this, that the source of a light when it passes through a monochromator, that is a light is a polychromatic. It contains many kind of it does not have a very fixed wavelength. So when it passes to a monochromator which have a fixed wavelength value, and then it passes through a sample and it transmitted light which is detected by a detector. So this is used to measure the absorption, and it is known as and this study is known as absorption spectroscopy. ओके, तो मेनली स्पेक्ट्रोफोटोमीटर के अंदर में हम ऑप्टिकल डेंसिटी को मेजर करते हैं इन टर्म विद द हेल्प ऑफ द जनरली रेफरेंस सैंपल्स. यहाँ पर ये होता है कि हम एक स्टैंडर्ड सैंपल कंसिडर कर लेते हैं जिसका हमें ओडी मालूम होता है, एंड नाउ वी आर बाय नोइंग एंड नाउ we are just measuring the OD of our tested sample, and then from this OD value we are going to calculate the concentration of the unknown sample, which is by help of a formula, that is concentration of the unknown sample is equal to OD of unknown into concentration of standard slash OD of the standard. Okay, so now we are here that principles of UV visible spectroscopy. It is a very simple generally principle. Okay, so UV radiation extends from 10 nanometer to 400 nanometer, and visible radiation region extends from 400 nanometer to 800 nanometer. It is very simple that एक certain amount की UV और visible के अंदर में वो wavelength absorb करेगा, and then it gets excited, and then the graph is plotted against the absorption, and the graph is plotted between the absorption and the frequency or a wavelength, and it is and here we can calculate the unknown concentration of the sample. जो common solvent यहाँ पे use करा जाता है वो होता है ethyl alcohol और hexane. Okay, so there are, as I mentioned earlier, that when a molecule or an atom absorbs a certain kind of a light of fixed wavelength or frequency, it gets excited from its ground level, and so there are 6 possible kinds of a transitions can happen. We are going to mentioning it one by one. So first of the type is sigma to sigma star transition. Here star is the anti-bonding orbital, and a normal sigma is considered as bonding orbital. So we are going to read it like this, that sigma bonding to sigma anti-bonding transition. So first, it is a first type, that in which the sigma electron from an orbital is excited to the anti-bonding orbital of sigma. Example है इसका methane, because it has only CH bonds, it can undergo this kinds of a transition, and so absorption maximum, that is lambda max, is at 125 nanometer. Generally, this kind of a transition is not seen in typical UV or visible spectrum because of its high absorption maximum. Okay. The second type is pi to anti-bonding pi transition. Here the pi electron in a bonding orbital is excited to the corresponding anti-bonding orbital. Compounds which contains like alkenes, alkynes, carbonyls, nitriles, aromatic compounds undergo these kinds of transition. Here example, that alkenes can absorb a certain kind of a wavelength of having 170 to 205 nanometer. Now the third type is non-bonding orbital, that is n orbital to sigma star, that is sigma anti-bonding orbital. This kind of transition is shown by saturated compounds containing oxygen, nitrogen, sulfur and halogens like atoms, which is basically all these atoms have free unpaired electron or lone pair of electron. This transition is usually requires less energy than sigma to sigma star transition, and there the example, the number of the organic functional group with n to star peaks is small, that is 150 to 250 nanometer. Now the fourth type is n to pi star transition, that is in which an electron from a non-bonding orbital is promoted to anti-bonding pi orbital. Compounds containing functional groups such as cyanides, nitro and carbonyl groups undergo these kinds of transition. It requires minimum energy and having a lambda max at 300 nanometer. So as we can see here, that the energy is inversely proportional to the wavelength. Minimum the energy lambda will be greater. Now the fifth type and sixth type is far less common. It is sigma to anti-bonding pi transition and pi to anti-bonding sigma transition. these electronic transmissions are just theoretically possible. They do not seen very oftenly, or they do not even seen in practical. ठीक है. These kinds of transcription show absorption spectrum in above 200 nanometer, which is accessible to the UV visible. Okay, so there are certain kind of terms which is used in UV visible spectroscopy. First one is chromophore. Chromophore is that functional groups which containing the multiple bonds capable of absorbing radiations above 200 nanometer due to n to pi and pi to pi transition. So is in simple language वो मॉलिक्यूल्स जो कि फंक्शनल ग्रुप्स कंटेन करते हैं विच कैन एब्जॉर्ब ओवर 200 नैनोमीटर, like NO2, NO, CO, CN, cyanides, and carbon, carbon, and carbon sulfurs. Oxochromes, the functional groups which have the ability to change, which when attaches to a molecule, it changes the ability of a molecule of absorbing the incident light. बेसिकली एक सिंपल भाषा में कि इस तरीके के फंक्शनल ग्रुप जब कभी भी किसी भी मॉलिक्यूल के साथ अटैच होंगे, सो इट चेंजेस, इट इंटरफेयर्स विद द लैम्डा मैक्स. अनदर टर्म इज बैथोक्रोमिक शिफ्ट और रेड शिफ्ट. सो जब आपका एब्जॉर्प्शन मैक्सिमा लॉन्गर वेवलेंथ की तरफ शिफ्ट हो जाता है, इट इज नोन एज बैथोक्रोमिक शिफ्ट और रेड शिफ्ट. The compounds which can do these kinds of effects is like oxochrome compounds such as alcohols and methoxy. Isochromic shift, blue shift, when the lambda max compound shift to the shorter wavelength, it is considered as isochromic shift, and due to this effect is due to the presence of a group causes removal of conjugation or by changing the solvent. Another one is hyperchromic shift and hypochromic shift. Hyperchromic shift is a shift when absorption intensity of a compound is increased, and how it is increased when the oxochrome is attached to it. ठीक है. Hypochromic effect when the absorption intensity of a compound is decreased, it is known as hypochromic. It can be here shown by the graph, that is hyperchromic shift and hypochromic shift, red shift and blue shift. So red shift is when increasing the lambda max, blue shift when decreasing the lambda max, hyperchromic when absorption is increased, and hypochromic is when absorbance is decreased. Hyperchromic is due to the oxochromic effects, red shift is due to the oxochromic, blue shift and hypochromic shift is of following. Now instrumentation. So we need a light source here. Generally the light source is used, that is tungsten filament for the visible, and halogen lamps and carbon lamps. In previous times deuterium lamp and xenon lamp is also used, but they are kind of unstable, and also the radiations of the UV causes the generation of a ozone by ionization of the oxygen molecule, which is harmful for the technician and also for the samples. Filters are also used here. The filters are generally used in order to minimize the spectrum width. I'm not saying that it is converting a polychromatic light into a monochromatic light. It is just narrowing the spectrum. The light is still after passing through it, when a light is still considered as a polychromatic but having a very narrow spectrum. The filters are made up of gelatins. Here is the picture of a UV spectrophotometer. A monochromatous, it consists an entrance slit which admits the polychromatic light from the source. A collimating device is also needed, which is a lens of a mirror which reflects the polychromatic light to the dispersion device. Wavelength resolving, as I previously mentioned that the prism, when a normal light or a polychromatic light passes from the prism, it is separated according to its lambda. Another focusing lens or mirror is used, exit slits, sample or cuvettes. Cuvettes is made up of quartz or fused silica to absorb UV radiations. Okay. Now there is two kind of a spectrophotometer, single beam and double beam. Single beam, as it mentions, is considered a single beam. This single beam is first passes to the reference cells, and by which the absorbance is set to the 0, and then this single beam is passes to the sample cell and measure its absorbance value. It is very early of design and is still used in both teaching and industrial labs. As seen in the figure, the light is passed from the source, entrance slits, and dispersion divisor and exit slits. They all are a part of a monochromator. And so first, the sample is a reference sample of by which by the help of which we set the spectrometer photometer at a zero absorbance value, and after that we are going to fill it with our tested sample and measure its absorbance value with the help of a detector. Now the double beam, it considers two kind of a light. In this kind of a spectrophotometer, simultaneously both reference sample and tested samples are being tested. A single beam is divided into the two ways. One is passes through the reference sample and other is passing to the uh, tested sample, as seen here. And there are two kind of a beam is generated. One is from reference sample and other is from the sample cell. Then the photodetectors, difference amplifiers, and the readout. So photo cells are made up of cadmium sulfides and silicons and seleniums. Electron passes through the selenium to silver, and silver acts as a collecting electrode and steel plate as another electrode. Phototubes, which is enveloped with the quartz window. Centrally situated metal wires act as anode and semicircle cathodes. Photomultiplier, they are designed to amplify the initial photoelectric effect and are suitable for the use at very low light intensity. Then photodiodes are the semiconductors that charge their charged voltage upon being struck by the radiation. The voltage is converted to the current and it is measured. So UV and visible is very simple kind of a spectroscopy in which light is observed at the UV and the visible spectrum, and then the absorption intensity is measured of the compounds. Two kinds of spectrophotometers here, single and double. Single beam, in single beam, firstly the beam passes from the reference cell, set the instrument at the zero absorbance, and then it is passed to the tested sample and the absorbance values is measured. In the double beam spectrometer, simultaneously the beam is divided into two parts. One beam is passed through the reference cell and other beam is passed through the sample cell. Simultaneously the value of both the samples is measured. Now next come to the fluorescence spectroscopy. In fluorescence, so there are in two kinds, absorption and fluorescence. Let's get started. Let's understand it with the help of a figure. So S0 is considered as a ground state. So as I mentioned earlier, whenever a compound is absorbed a wavelength of a light of a certain kind of a wavelength and a frequencies, its electrons are excited from its ground state. So in both the figures we can see that the electron is absorbed, the light is absorbed and the electron is excited from its S0 to S2 एंड S1 ऑल्सो. सो आप यहाँ पे देख सकते हो कि S2 तक और S1 तक दोनों फिगर में गया. इन केस ऑफ एब्जॉर्प्शन हम क्या देखते हैं कि एब्जॉर्प्शन यहाँ पे क्या है कि एच न्यू ए, कि जो आपने लाइट एब्जॉर्ब करी थी उसी ही की एनर्जी को आपने कंसीडर करा. सो अब ये इलेक्ट्रॉन F2 तक तो रहेंगे नहीं, ये इलेक्ट्रॉन नीचे भी आएंगे एंड इलेक्ट्रॉन जो नीचे आएंगे यानी कि F2 से S1 एंड ग्राउंड स्टेट पे भी आएंगे व्हेन दे लूजेस all their energy. And how they gonna lose it? By releasing the light of certain wavelength or frequency, and that emission is considered as fluorescence. Here H nu f. So when it comes to when it's come down from S1 to S0, it releases a certain kind of a light of certain frequency which is considered as nu f, and the energy of the electron of that photon is E equal to H nu f. In fluorescence spectroscopy we are dealing here at H nu f, and the graph is plotted against this H nu f and this and the emission light wavelength or frequency of energy. सो अगर एक सिंपल फ्लोरोसेंस प्रोसेस के बारे में बोले, सो सबसे पहले फ्लोरोफोर वो मॉलिक्यूल जो कि लाइट को एब्जॉर्ब करेगा और लाइट फिर बाद में इमिट भी करेगा, दैट इज कंसिडर्ड फ्लोरोफोर. तो एक्साइटेशन ऑफ अ फ्लोरोफोर थ्रू द एब्जॉर्प्शन ऑफ लाइट एनर्जी आर ट्रांजिएंट एक्साइटेड लाइफ टाइम. तो सबसे पहले वो एक लाइट एनर्जी को एब्जॉर्ब करेगा, फिर उसके बाद में ट्रांजिशन में जाएगा एंड देन इट रिटर्न्स टू द ग्राउंड स्टेट accompanied by the emission of a light. Light energy emitted is always of a longer wavelength than the light energy absorbed due to the energy loss due to the transient excited lifetime. सो यहाँ पे एक सबसे बड़ी बात इस पॉइंट में बता दी गई है कि जो लाइट एनर्जी एमिट होगी वो लॉन्गर वेवलेंथ की होगी ऑलवेज एज कंसिडर्ड एज कम्पेयर टू द लाइट एनर्जी एब्जॉर्ब्ड. और ऐसा इस वजह से होगा बिकॉज ऑफ द एनर्जी लॉस ड्यूरिंग द एक्साइटेड लाइफ टाइम ट्रांजिएंट. Here is the fluorophore molecule which absorb energy and then it get excited, and when it return back to its ground state it emit certain kind of a light of certain frequency and this. So here the absorption and emission graph. So there is a difference here at the of the absorption and emission graph, that is the wavelength is plotted on the x-axis and the energy of the absorbed light and emission light is plotted on the y-axis. So there is a difference between these two, and that shifting is known as Stokes shift. So instrumentation source monochromator चाहिए होता है which converts a polychromatic light into a monochromatic. Then sample cell slits से pass होंगे emission monochromatic detector amplifier and recorder. एप्लीकेशन जनरली जो फ्लोरोसेंस स्पेक्ट्रोस्कोपी के बारे में अगर हम बात करें तो फ्लोरोसेंस स्पेक्ट्रोस्कोपी आपकी कन्फर्मेशनल चेंजेस को अंडरस्टैंड करने में आती है, जैसे कि एटीपी हाइड्रोलिसिस होना, कोई किसी मॉलिक्यूल जब हम बात करते हैं कि जो हम एंजाइम्स के अंदर में कंसीडर करते हैं लॉकेन की हाइपोथेसिस पढ़ना, कन्फर्मेशनल चेंजेस आ जाना है और मेम्ब्रेन डायनामिक्स की स्टडी करना. सो ऑल दीज थिंग्स आर बेसिकली स्टडीड विद द हेल्प ऑफ द फ्लोरोसेंस स्पेक्ट्रोस्कोपी. There are two types of there are certain kind of proteins which can use as for the fluorescence study. So there are intrinsic protein fluorescence proteins which consist three fluorophores: tryptophan, tyrosine and phenylalanine. As we all know that these these amino acids can absorb 280 nanometer की ये light को absorb कर सकते हैं, जिसमें कि फिनाइलएलानाइन बहुत कम होता है, ट्रिप्टोफैन एंड टायरोसिन ज़्यादा होते हैं. ठीक है. So intrinsic protein fluorescence is usually determined by tryptophan fluorescence, which can be selectively excited at 295 and 305 nanometer. Excitation at 280 nanometer excite tyrosine and tryptophan fluorescence, and the resulting spectrum might therefore contain contributions of both types. The main application for intrinsic protein fluorescence aims at conformational monitoring. We have already mentioned that the fluorescence properties of a fluorophore depend significantly on environmental factors. So अब यहाँ पे हम कई तरीके की हमने एक्सटेंसिव फ्लोरोसेंस डाइज भी बनाई है विच इज़ यूजफुल. कि होता क्या है कि अब जैसे कि अब ट्रिप्टोफैन, टायरोसिन और फिनाइलएलानाइन जैसे मॉलिक्यूल्स तो आपको नेचुरली कुछ आपको आपके कन्फर्म सैंपल में मिल जाएंगे, बट कई ऐसे सैंपल्स भी होते हैं जहाँ पे हमें कन्फर्मेशनल स्टडीज़ करनी है, बट उन सैंपल्स के अंदर में किसी भी तरीके का कोई फ्लोरोफोर मॉलिक्यूल नहीं होता. तो उस कंडीशन के अंदर में हम एक्सटेंसिव फ्लोरोसेंस हमने डाइज क्रिएट करी है आजकल के ज़माने में, जो कि आपकी नॉन कोवेलेंटली बाइंड करती है विद द मॉलिक्यूल्स एंड देन दे आर यूजफुल इन स्टडिंग द कन्फर्मेशनल चेंजेस इन दोज molecules. So for making an extensive fluorescence molecule, three criteria must be fulfilled. Firstly, it must not affect the mechanistic properties of the system under investigation. सबसे पहला बिल्कुल आइडियल कंडीशन है कि जो आप फ्लोरोसेंस मॉलिक्यूल एक्सटेंसिव फ्लोरोसेंस बना रहे हो, इट डज नॉट अफेक्ट्स इट्स मैकेनिस्टिक प्रॉपर्टी, कि मॉलिक्यूल की नेचुरल मैकेनिस्टिक प्रॉपर्टी अफेक्ट नहीं होनी चाहिए. सेकेंडली, जो फ्लोरोसेंस emission needs to be sensitive environmental conditions in order to enable monitoring of them molecular event. And lastly, the fluorophore molecule must be tightly bound at unique locations. There are some kind of extensive fluorophore red जैसे Congo red, thioflavins, Nile red, DCVJ, and here are the structures. These structures are also mentioned at NCBI site. Thank you.